Okay, let's make a start. Can someone just shut up? I want to finish off section B by discussing the Cayley Hamilton Theorem. I've discussed who Cayley was, okay, a number of times. He's come up in chapters 1, 2, and Sylvester's as well, but haven't discussed Hamilton. William Hamilton was an Irish mathematician, okay. What do you call it? He's also took up languages. By the age of 5, he knew Hebrew, Latin, and Greek pretty well, okay. So he's a child prodigy of languages. But he did turn to mathematics quite early on in his life, and there's a famous bridge in Ireland where you can see this formula. You don't see formulas in bridge, or when you go for a walk, do you? You might see Nelson's column or something, or other landmarks, but you won't see a formula, will you? Highly unlikely you're going to see a formula. But you will come, if you went to Ireland, you'll see a formula which say something about dimension 4. And we might discuss this in MT1, but I'm not going to discuss this formula now. There's a little plaque there, it stands there. I mean, this is where he thought, when you go, like I say, mathematics is one of those subjects which you can do. You don't need to have a lab to work in or some experiments to work in. You can do quite a lot of mathematics when you're walking about, when you're having a shower or whatever. Yeah, okay. And this is when when he went for a walk and he came across this inspiration about a formula for things about vectors in dimension 4. Okay, he was a bit of an alcoholic as well at the same time, but you can read more about what's his name, more about his biography. He was in that on page 513. He also tried to find like the complex number is close related to 2D, yeah, to R2, yeah, okay, to 2D space, okay. He goes, is there another complex number, hypercomplex number, which is closely related to 3D space, okay? And well, there's a couple of problems with that. The one problem is if you do vector product, you don't get commutativity or association, so you can't switch them around. That was the problem. With 2D, you can switch them around, okay? And that was the issue he came across. And he tried for quite a long time to find a 3D, hypercomplex number which related to 3D space, and it couldn't be done because of, it didn't tie in with the rest of algebra. Anyway, the Cayley Hamilton theorem gives you, tells you gives you a simplified way of how to work out things like A5. Say you want to work out A is a matrix 1, 2, 3, 4, and you want to work out A5. Okay, how would you say if you're given A is equal to 1, 2, 3, 4? How would you work out, A or A to the 10? How would you work out A to the power 10? And like I said, you don't really want to. Let me switch that. Can you all see that? Not too much light. Not too sure which is better. Okay, A to the 10. You don't want to do 1, 2, 3, 4 times 1, 2, 3, 4 times 1, 2, 3, 4. You don't want to do 10 copies of A. Okay. Now, Cayley Hamilton theorem reduces how you do powers of matrices. That's why it tells you. That's why Cayley Hamilton is there. That's why we need it. Otherwise, say, what's the point? You might argue, why should we bother with Cayley Hamilton when we've got lots of other theorems? Why learn another one? Well, it does tell you how you can evaluate A to the power 10 much easier than doing. At the moment, the only tools we have. If I asked any of you to work out A to the 10 in an exam paper, those tools you have is 1, 2, 3, 4. That matrix A times A times A times A. That's the only way you've got it, and you're bound to get it wrong, and so would I. And it wouldn't be set as an exam question. But if you look at past exam papers, I've set you matrices, okay, where it says A is this, work out A to the power 10 or A to the power 5 or whatever. And some people have done it by brute force, okay, just so they don't understand what's going on. They shouldn't do it by brute force. So now I've set it in such a way that you can't do it by brute force. So it'll be instead of A to the 5, it's like A to the 10. So you cannot use brute force, A times A times A times A times A. Okay, what does Cayley Hamilton theorem? Well, what it says, this is the the statement of the Cayley Hamilton. What it really means is that every, okay, hang on, let me write it down. If you've got a characteristic polynomial, okay, p lambda, okay, is given by, I don't know, lambda n plus cn minus 1 lambda n minus 1 plus c1 lambda plus c naught, okay. Cayley Hamilton theorem says the matrix also obeys this rule. So you equate this to 0, okay. It says if you take the matrix A, if this is the equation, the characteristic equation, okay, you'll find that PA is also satisfies a to the n plus cn minus 1 a to the n minus 1 plus c1a plus c naught I, of course, kind of is equal to 0. That's what it says, okay. That's what Cayley Hamilton theorem more or less says. Let's do it for an example. Say you're given the matrix A, given that A is equal to, what is it? 3, 2, 3, 4. Illustrate Cayley Hamilton. Okay, so first what we're going to do is find the characteristic equation, the lambda, the eigen. How do you find that? How do we find this p lambda here? How do we find that? Come on. How do we find the lambdas? How do you find the eigenvalues? Yep, Patrick.
What you would do is you need to do the A minus.
Yeah, determinant of A minus
lambda I.
Exactly. Yeah, that's what we do. Okay, so work out the determinant. Okay, of. Zoom into this a bit. Determinant of A minus lambda I, which is the determinant of what? What does it come down to? Go on, Patrick. No,
it's going to be 3
yeah.
minus lambda.
Yep.
2.
2, yep.
And it's going to be 3.
Yep.
And it's going to be 4 minus
yeah,
lambda.
4 minus lambda, isn't it? Yeah. Okay. How do we work out determinant of 2 by 2? How do we work out? Yeah, this diagonal and take away the other diagonal, isn't it? Yeah. So it's going to be 3 minus lambda, 4 minus lambda. Okay. Take away 6. Yeah. Now, remember, what did I say about expanding these? What should you do? So it's easier for you. In this case, not much easier, but slightly easier. Go on then, Patrick.
You can take the minuses.
Yeah, we like x minus 3 rather than 3 minus x, don't we? We like that, don't we? We're used to x minus 3 than 3 minus x. Okay, so take 2 minuses out. So minus minus. So what do we get? What do we get inside? Come on, no, someone else should be able to do this. If you take a minus from here, what do you get? Go on then. Yeah, lambda minus 3, yep. Lambda minus 4, okay. Minus 6. Minus minus gives you plus. So what do we get? That's plus, isn't it, clearly? That's equal to plus. Oh, why doesn't it focus? Good thing about this, I can see exactly what you can see before I have to look round all each time. What do we get? Come on, you should expand that. What do we get if we expand this? Lambda squared, yep. Minus 7 lambda, 3, minus 4, minus 3, minus 7 lambda, yep. Sorry? I can hear a mouth, but I can't see one. Where is this mouth?
That's 12.
Plus 12, yeah. Plus 12, it was a female, so that's someone else. Plus 12 minus 6, yeah? Plus 12 minus 6 gives you what? Yeah, plus 6, isn't it? Yeah, plus 6. So, okay. How do we, if we factor, well, that's it, isn't it? Okay. That's equal to 0, don't we? Okay. Now, what does Cayley Hamilton's theorem say then? What does Cayley Hamilton say? Come on. In this instant, we want to show it. I'll show it in a second. But what do we need to show? You're always late every time. Yep.
I think to show like the lambda, like what lambda squared then 7.
No.
You know, like the C0 equals to 6.
Yes. Yeah. Yes. Okay. But how does it? What does Cayley Hamilton theorem say? We need to show what? Look, I've said it shows P lambda is equal to this, yeah? Is equal to 0, yeah? Okay? And PA is equal to, it satisfies that equation. So what do you think you're going to have? Yeah, exactly. Put A in there, yeah. Put in, so lambda, you should need to show that A squared minus 7A plus, not 6, but 6 what? 6I is equal to the 0 matrix. That's what we want to show, don't we? Yeah. Okay.
Yeah.
Or we can show that A squared is equal to 7A plus 6I. You can show either one, can't you? Yeah. Do you agree?
No,
Okay. Well, same thing. Oh, minus. Yes, good. Well done, Patrick. Yeah. Minus. Okay.
Yeah.
Yeah. I was telling you, I don't make any mistakes, but you caught me out there. Okay. So it's minus. Yeah. Okay. We can show either of them. We can either show A squared. Okay. Minus 7A plus 6I is equal to 0, or we can show A squared is equal to 7A minus 6I, can't we? Yeah. All right, let's show this one. Doesn't matter which one you show. Let's try to show that, shall we? So let's work out 7A minus 6I. Well, 7A. So 7A minus 6I is 7 times, what is it? The matrix given to us is 3, 2, okay, 3, 4, minus 6 times 1, 0, 0, 1, isn't it? Yeah. Okay, so what do we have? 7 times, so we have 7 times 3, which is 21, isn't it? Yeah? 21 minus 6, do you agree? The first entry? Minus 6, okay. 7 times 2 is 14. 14 minus 0, isn't it? Yeah? Okay, 14 minus 0. Okay, and then we have 7 times 3, which is 21 again. 21 minus 6 times 0 is 0, okay. 7 times 4 is 28 minus 6, isn't it? Yeah? And what does that simplify to? We simplify that. What do we get? Come on, it's just simple subtraction.
15.
Yeah, 15, 14, yep, carry on. 21, 22, yeah? So now we've shown that 7A, okay, if you look at this, we've shown, oh no, I don't want to go the other way, don't I? I want to show that, so 7A minus 6I is equal, 7A minus 6I is equal to this, isn't it? Okay, I want to show A squared is the same one, same thing, don't I? Yeah. Okay, how do I show A squared? Well, A is equal to, A is 3, 2, so A squared is 3, 2, 3, 4 times 3, 2, 3, 4, and it should come to this. We don't engineer it, but let's see if it does come to this. We don't engineer it, okay? It should come to 15, 14, 21, 22, yeah? Okay, so what do we get? 9 plus 6, 15, okay? Second entry, 6 plus 8, 14, okay? 9 plus 12, 9, look, 3 times 3 is 9, plus 12 gives you what? 12 plus 9 is what? 21, okay? 6 plus 16, 22, yeah? All right, 22. And there you go. If you look at the A squared minus 6I, okay? No, sorry, 7A minus 6I gives you that, and A squared gives you that, yeah? So we show Cayley Hamilton, this matrix satisfies Cayley Hamilton, but like I said, if you look at the proof, it's done it for all the matrices. Every matrix, you know, it's the case. Now, like I said, is that what we want to do is really work out, you know, we want to use this idea, this Cayley Hamilton idea, to work out powers. I mean, this is not much use to you, if you think about it. You can say, well, so what? You might argue, so what? But if you've got a matrix A, let's say A is equal to, I don't know, let's say 0.9, 0.2, 0.3, 0.6, then A to the 100, of course, you wouldn't do that by hand. Okay, if you put it into a computer, they wouldn't. Nor would a computer do, you know, A times 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 A. It wouldn't do that neither. The computer wouldn't do that. It'd take up too much time. It really would take up too much space as well. And if you work at A to the 10 on, I don't know, MATLAB or whatever, any software, you get 29.4. This is to 1 dp, 13.5, 20.2, 9.2. That's what you get. Now, I either use Cayley Hamilton or I use some other something else that we're going to discuss in sections C and D as well, okay? There's other ways as well. So I either use Cayley Hamilton, okay? But it's definitely not going to do A times A, because that'll, you know, you can imagine that's going to take up a lot of memory space and a lot of time. You know, you want A, and you know, you want it within milliseconds, don't you? You know, you enter A as a matrix, you want to look at 800, and it gives you the answer within milliseconds. So any software is not going to do A times A times A, definitely not. So let's see how this works. Let's see how this works for one particular, any matrix. How do we find it? Let's say we're given A. This is example 12. Sorry. A is equal to. Let's say A is equal to 2 minus 4, 1, 3. Find A to the power 4. And I don't want to do it. I mean, this one you could do by brute force, but I don't want to do it by brute force. I really don't. It's not too big, but if I say A to the 10, you know, let's do it by. So how do we do this? How do you think? Oh, okay, I'll tell you one thing is that you want to. I'll give you a clue. I'll give you a hint. You want to use Cayley Hamilton. So how do we find Cayley Hamilton? What's Cayley Hamilton say? Patrick, yeah.
Well, firstly, you want to find the
yeah, the eigenvalues. Okay, yeah, okay. You don't actually find. You just find the equation, don't you? Really, okay. All you're going to do is find the equation. Yeah. Now you can do this in your own time, but you'll find that P lambda. If you do what we just did in the first, you know, the first one, you'll find that P lambda, okay, comes to. I mean, you can do this in your own time. Lambda squared minus lambda minus 2. Okay. If you work it all out, this is what you're going to get a quadratic because it's 2 by 2. If it was a 3 by 3, you'd get a cubic. Okay, but this is what you end up with. All right. So what does Cayley Hamilton say? Come on, you're going to tell me now. Yeah, PA is equal to A squared minus A minus 2I is 0, isn't it? Yeah. Okay. Yeah, you agree with that? Okay. So if we want to find A4, yeah, what's A squared equal to?
So A squared is equal to
yeah,
A plus 2I.
Yeah, A plus 2Y, isn't it? Yeah.
Yeah,
take that across. So what's A to the So
would you just try and like double it?
Yeah. Well, no, square it. Yeah. Square it. Okay. Yeah. Double it means something different. A to the 4, of course, is A squared, isn't it? Yeah. Okay. So if we square that, so if we work out A plus 2I squared times A plus 2I, yeah? If we work that out, yeah? A squared, yeah? Okay? So A squared is equal to A plus 2I, look there, yeah? Okay? Square it, you know, times it again. Do you follow that step, what I've done there? Okay? Now how do we work this out? How do we expand this?
You need to work out A plus 2I first.
Well, A times 2I is going to be, guess what's that going to be? What's A times I? It's the 2 you can park outside, can't you? What's A times I? No, not 0. I is not 0. No, what's it going to be? A times I, what's it going to be? It's going to be A, isn't it? Yeah? It's a density. It's like, remember, the density matrix is like multiplying by 1, okay? It's the density. So, okay, A times A, what's A times A? A squared, yep, A squared. A times 2I is what? What's that going to be? Yeah, 2A. Well, I you don't need because, yeah, okay. It's 2 plus 2A. 2I times A is going to be what? Yeah, plus 2A. And what is the last one? What's that going to be? Yeah, plus 4I squared. And of course, I squared, I times I, you know, I squared is going to be I, okay? So what's this come to? A squared, yeah? Not A4, I'm sorry. This is A squared plus 4A plus 2I, yeah?
Why is it plus 2I?
Oh, 4I, sorry. Hang on, let me write this. So it's A squared, yeah?
Yeah.
That's 4, isn't it, yeah?
Yeah.
It's plus 4a plus 4i, because I times I squared is I cubed is I, I to the power 10,000 is I, yeah? Okay, it's like 1 times 1 to the power a million is I, isn't it?
Yeah.
It's 1, isn't it? Same idea here. Okay, you can work it out if you want. So what's a squared equal to? What's a squared equal to? I can work out a squared, or we can do even easier than that.
Yeah.
What can we do? Something which you, all right, you can't, so you can, yeah, go on.
Yeah, you can just put it as a plus 2y.
Yeah, of course, a squared is equal to a plus 2i, isn't it? Yeah?
Yeah.
Okay, so you get a plus 2i plus 4a plus 4i. And what does simplify to?
5.
Yeah. 1a plus 4a gives you 5a, doesn't it? Yeah? That's 5a plus what? Yeah, 2 plus 4 plus 6a. So a to the power 4 is that, isn't it? That's what it is. That's what it is. Okay, so you're not doing a times a times a times a. You're not going to do that at all. This is much easier.
Yeah.
Okay, now what you do is multiply a by 5 and add 6i. Okay, what's 5? So a4, 5a, 5a is given to us, isn't it? A is the matrix which is given to us. So 5, that was minus 2, minus 4, 1, 3, yeah? Plus, so 6i equal to? Yeah, 6006, isn't it, yeah? Okay, 6006, yeah? Okay. So what do we get? If we simplify this, what do we get? 5 times minus 2 gives you what? Yeah, minus 10 plus 6, yeah? Minus 20. 5 times minus 4 is minus 20 plus 0. 5 plus 0. Okay, 15 plus 6, yeah? 15 plus 6. Okay, work that out. You'll get, what do we get? You simplify that. Sorry? Yeah, minus 4, yep, go ahead. Minus 20, yep. 5 and 21. So that's what A4 is equal to. Okay, see? We've done a bit of algebra. That's what we've done. We didn't do such a thing you don't want to do. It's quite laborious to do A times A times A times. Now you can work out A5 and A6 quite easily now. Okay? It's quite, once you work out A4, you can work out all the others.
Yeah.
Okay? All right. One other, what is, like I said, I've asked this question before, Patrick's answer, so let's see if someone else can answer it apart from Patrick. What is the most laborious thing to do in linear algebra? Yeah, find the inverse. We don't want to find, we want to find the inverse, but we don't want to use all those cofactors and all that, or trying to use gas elimination, get the right hand. And we don't want to do that, okay? We want to do an easier way of finding the inverse. Can we find an easier way? Again, Cayley Hamilton helps there. Cayley Hamilton tells us how we can find the inverse much easier than trying to, try and find all the cofactors and all that, okay? Because we do know that Cayley Hamilton, equation is the equation, or the characteristic equation of that matrix, isn't it? Okay, so let's see if we can find the inverse of a 3 by 3, like I say, or a 4 by 4. 2 by 2 I would never do the way we normally do it. But if it's 3 by 3, 4 by 4, this is much easier. Say if you're given A is equal to 10, 15, 0, 2, 4, 0, 3, 6, 6, yeah? And you're told that P lambda is equal to lambda cubed, of course it's going to be cubic, minus 20 lambda squared, plus 94 lambda, minus 60. You're told that, or, you worked it out. Listen, I'm not going to say waste my time doing eigenvalues, eigenvectors all over again. So how do we, how is this going to help? Sorry, the question, what's the question? Find A minus 1. Our question is to find the inverse. Now, like I said, for 3 by 3, you've got 9, you've got to find all the cofactors and so on, and transfer them, find the determinant as well. Don't want to do that, I want to do it in an easier way. You work this out, okay? What can you say about, what do you call it? What can you say, well, what can we say about A? What does A satisfy then? Use yeah, go on, Mike. Go on, Patrick.
So that'll be A cubed.
Yeah, A cubed minus
20A squared.
Yep.
94A.
Yeah.
minus 60i
Yeah.
equals to 0.
Is equal to 0, isn't it? Yeah, is equal to 0. So, right, how does it help? How are we going to find the inverse of A from this? What is the inverse of A? What does it satisfy? Say it was called B. What would AB satisfy? Say if the inverse, let's say you had AB, B was the inverse of A. What should it satisfy? It's got to equal I, doesn't it? Yeah? And we've got an I there. Look, there it is. Haven't we? So, what could we do? Sorry? Yeah, take it to the other side. Exactly, take it to the other side. So then you have A cubed, yeah? Minus 20A squared plus 94A is equal to 60I, yeah? Okay? But 60 is too big. You want I, so what do you do?
Divide it all by
Divided by 60, yeah, of course. So 1 over 60, A cubed, yeah, okay, A cubed minus 20A squared plus 94A is, no, not is equal to 0, is equal to I. Now that's good, but we haven't got, we need, look, it's A times B. We need an A out here, don't we? Do you agree? We need A times something, don't we? How do we get the A? Common, it's obvious, isn't it? Yeah, of course. A is common. Look, A is there, A is there, A is there, isn't it? Can't you? You can take it out, can't you? Okay, so take out A, so you got A, and then you get 1 over 60. What do you get inside? Yeah, A squared minus 20A plus 94I, isn't it? Yeah, 94. I'll be with you in a second. Yeah, 94I. Sorry, yeah, go ahead.
No, I was going to say the next bit.
Sorry?
I was going to say the next bit.
Oh, okay. All right, okay. Well, you said the next bit. What's the inverse equal to?
It's going to be that 1 over 60.
Yeah, it's going to be that. That's going to be your inverse, isn't it? Huh? Yeah, A times B is equal to I, haven't you? Yeah? That's going to be your inverse. So we haven't found any cofactors. No cofactors. You know, none of this gas elimination, getting all the rows in order, so we get, you know, the right-hand side, about 9, 10, 20 operation or whatever it is. Okay? That is equal to A minus 1. That is your inverse, yeah? That's what you, so all you've got to do is you've got to work out A squared minus 20A plus 94I. That's what you've got to work out, and that'll give you a, you know, I mean, that's arithmetic now, isn't it? You should be able to do that. A squared, you know, square this matrix, you know, 10, 15, 0. I'll let you do that if you want the calculation. Okay, it's still tedious from then, but not as tedious as, you know, if you work it out, this is what you get. Okay, this is what you get. Okay, so the Cayley Hamilton theorem, where's that? Is useful for finding the inverse, okay, and also to find powers of matrices. Okay, we want to find powers of matrices. It's useful in that respect.